The broadcast is now starting. All attendees are in listen-only mode.
Hi there, and welcome from Ventura, California to today's GNSS Performance Standards and Certification Beyond Spectrum Protection, sponsored by Spirent and Inside GNSS and hosted by WebAttract, your end-to-end solution provider for informational webinars. I'm Lori Dearman, Senior Webinar Producer with WebAttract, and I'll be one of your moderators for today's session. And in just a moment, we'll be introducing our panel of thought leaders, as today's webinar is about hearing from these experts as they explore the history, current status, and prospects for GNSS receiver performance standards. You'll also have an opportunity to have your questions answered at midpoint and at the end of the presentation during the Ask the Experts panel session with all of our panelists. Now, we've invited you along with over 450 professionals from 43 countries, 28 states and provinces, representing the industries that you see up on the screen. Over the next 90 minutes, regardless of your industry segment or your location, we're confident that you'll find today's webinar of value. Before we get started, Glenn Gibbons, editor and publisher with Inside GNSS, would like to take a moment to welcome you and introduce Steve Hickling of Spirent and Demos Gebra Egzabher, who will be moderating the main portion of today's webinar. Glenn?
Thank you, Lori. And greetings to our worldwide audience from all of us at Inside GNSS magazine. This latest presentation in the Inside GNSS web seminar series is sponsored by Spire Communications, and it addresses a subject facing the GNSS community that is both new and old. That is GNSS receiver performance standards and the possible introduction of requirements to certify user equipment. Inside GNSS reaches more than 35,000 readers around the world with its print edition and thousands more with our digital magazine and newsletters. Based on the number of registrations for today's webinar, it's clear that GNSS receiver performance standards is a matter of considerable interest to many of you. Our webinars follow the same principles that we bring to the engineering-oriented articles in our publications, to take up issues of current importance to the GNSS community and to invite subject experts to help us explore those topics in depth. So now I'd like to introduce Steve Hickling, lead product manager for Spirent's GNSS simulator business, to say a few words about today's event. Steve?
Thanks, Glenn. Whenever there's a performance expectation, it seems reasonable that that expectation is matched by a standard and a method to certify to that standard. Spirent obviously approached this issue from the perspective of a test solutions provider with a background both in conformance and performance testing. So this whole topic is one that I'm really excited to be learning more about, and very pleased and proud that Spirent are able to assist in this way. As Laurie said at the outset, a large part of this is going to be your questions as well as hearing from the experts. So I'm really hoping you're going to participate there. And I look forward to hearing your questions and the experts' opinions. Glenn.
Thank you, Steve. Now, our moderator for today's web seminar is Demos Gebra Egzabher. Demos is an associate professor of aerospace engineering and mechanics at the University of Minnesota, Twin Cities campus. His research deals with the design of multi-sensor navigation and attitude determination systems for aerospace vehicles. Recently, Demos' work has focused on multi-sensor solutions for operations in GNSS stressed and GNSS denied environments. Demos, it's great to have you with us again today. Welcome.
Thank you, Glenn, and a warm welcome to everyone. Welcome to today's Inside GNSS webinar on GNSS performance standards and certification. We've got lined up today for you leading experts, three leading experts in this area, and they'll talk about important issues related to this very important and topic of significant interest today. Before we get in, though, to the webinar itself, as a quick icebreaker and to get a sense of our audience out there, we'd like to do a quick poll. Lori, if you would put the poll question up.
Absolutely. And folks, coming up on your screen is that first question. We'd like to hear from you. My understanding is that GNSS receiver standards and certifications are primarily aimed at ensuring that, and go ahead and pick one of the following: GNSS receivers work as intended when used, wireless devices don't interfere with GNSS, or perhaps you think both, or as states all of the above. Looks like it's coming in at 42%, picking GNSS receivers work as intended when used, and just over half, 55%, with all of the above. Demos, how's this aligning with what you were thinking?
All right, so again, as you're going to see from today's webinar, it's going to actually, the standards are going to apply to both questions, and again, our presenters will will address both of these issues. So with that, let me introduce our panelists, our webinar presenters, and get into the webinar itself. Our first presenter is going to be Jules McNeff, who is the Vice President for Strategy and Programs at Overlook System Technologies in Vienna, Virginia. He has extensive experience in the GPS and GNSS world, where he has served as a GPS Program Element Monitor at the Air Force Headquarters and the Pentagon from 1986 to 1989. And then as the GPS focal point in the Office of the Secretary of Defense, C3I, and Acquisition and Technology from 1989 to 1996. And then in industry as a supporting the National Security Space Architect from 1996 to 2002, and then as a special assistant to the NASA Administrator from 2002 to 2003, also as the OSD Network and Information Integration and DoD Chief Information Officer from 2003 to present. Our second presenter is going to be Chris Hegarty, who is the Director for Communications, Navigation, and Surveillance Engineering and Spectrum at the MITRE Corporation. He's played an instrumental role in the selection of the frequency for the GPS third civil signal, L5. He also led the co-development of the specifications for this signal and served on a U.S.-European technical working group that helped produce agreements on the common L1 civil signal design. Mr. Hegarty is the chairman of the Program Management Committee for RTCA, the private not-for-profit corporation that develops consensus-based recommendations regarding communications, navigation, surveillance, and air traffic management system issues. And our third panelist is Ron Borsato, who is the principal architect at Spirent Communications, and he has 17 years experience with the wireless industry. He is the vice chair of the CTIA ERP ad hoc subgroup and also served as a technical advisor to the cellular subteam of the Lightsquared technical working group. He actively participates in 3GPP and LTE and OTA matters. Mr. Borsato served as the chair of the CTIA GPS subgroup during the development of the test requirements. So with that, let me hand it over to our first presenter, who's going to be Mr. Jules McNeff. Jules?
Thank you very much, Demos. This webinar addresses issues regarding GPS receiver performance and demands from some quarters for GPS receiver certification. Those demands grew out of recent experiences with Lightsquared and the misinformation and disinformation that characterized that debate. In my portion of this webinar, I'll cover the responsibilities of the participants in both government and industry, and the scope and range of options for GPS receiver performance certification processes that will likely be necessary regardless of whether they're desired. I also note that several categories of GPS receivers are already today subject to performance certification regimes of various intensity, and my fellow presenters will speak to the aviation and wireless categories respectively. First, I'll speak to the realities and obligations which should be accounted for by the government regulators of RF spectrum use at the Federal Communications Commission for commercial spectrum and the National Telecommunications and Information Administration for spectrum used by the government. One reality is that GPS is broadcast from satellites such that the received signal at the Earth's surface is well below the noise floor. Another is that, unlike communication signals, a GPS receiver must not only recover the bits in the navigation message, but also requires a level of what I'd call crispness in the reception so the receiver can use knowledge of the bit transitions to determine elapsed time between transmission from the satellite and reception from the receiver as indicated in the diagram. This is used to determine the pseudo-range to the satellite and ultimately the PNT solution. It's fair to say, though, based on personal experience, that government regulators do not feel a sense of obligation regarding these unique features and are inclined to treat them the same as communication systems. It is therefore incumbent on GPS users to continue to educate the regulators to the contrary. More on that later. At the same time, GPS users have realities and obligations of their own to acknowledge. The first is that GPS operates within narrow spectrum allocations assigned by the International Telecommunications Union to Radio Navigation Satellite Services, or RNSS, in the case of L1 as shown in the diagram. GPS is registered to operate between 1560 and 1590 megahertz, and no more. Further, there is increasing pressure for more efficient spectrum allocation with demands to access so-called underutilized spectrum adjacent to the RNSS. In this case, like the military, civil users can accommodate that reality by using new GPS civil signals that will be available in other parts of the L-band. Finally, recognize that the low-power GPS service cannot be made bulletproof to interference, and multi-source integrated PNT to complement GPS, as is already being used in some wireless services today, will be necessary for the future. When one looks at receiver certification regimes to address some of the realities I just mentioned, there are two primary sources of performance requirements to follow. The first is the technical performance of the GPS receiver itself, defined in interface specifications issued by the GPS Directorate and publicly available as shown. All civil signals are included, and the graphic illustrates just one small excerpt of the navigation message bit structure. This has caused problems in the past when manufacturers made assumptions about bit allocations that were not consistent with the specification. The second source of performance requirements is in those performance standards established by regulators of specific user applications that are enabled or augmented by GPS. My fellow presenters will address two of those application areas, and there will likely be more in the future. The following slide depicts the actual GPS receiver performance elements that are subject to either technical or application performance certification testing. The signal reception portion includes provisions for filtering, if appropriate, to minimize out-of-band effects within the GPS spectrum allocations. Signal demodulation, tracking, and processing, the next elements, are iterative elements that operate continuously to synchronize codes, detect data bit transitions, read the navigation message, apply correction factors as may be available, and calculate pseudo-ranges and the ultimate continuous positioning, velocity, and timing solution. Finally, the applications element establishes qualitative requirements that in many cases drive quantitative receiver design decisions. So while standardized technical performance certification is feasible against the GPS interface specs, there is no one-size-fits-all solution to the application performance certification problem. I have highlighted on the slide in red the two principal areas through which manufacturers and applications regulators can best affect GPS receiver resiliency to interference. That concludes my initial material, and I'm happy to turn the program back to Demis.
Thank you, Jules. So our next presenter is going to be Chris Hegarty, and he's going to be looking at the performance standards from the aviation point of view. Chris?
Okay, thank you, Demis, and good afternoon, everyone. In my first set of remarks for this webinar, I aim to provide a brief overview of the civil aviation community's experience with receiver standards and certification. To ensure safety, civil aviation has a long history of imposing performance standards and requiring certification not only for avionics but also for other critical components of an aircraft. As far as GNSS avionics go, standards were first adopted internationally by the International Civil Aviation Organization, which is a specialized agency of the United Nations that regulates civil aviation. They adopted these in 2001. The standards reside in an annex, which is called Annex 10 to the Convention on International Civil Aviation, which is a treaty signed in 1944 and now adhered to by 191 nations. These GNSS standards have subsequently been amended essentially annually 11 times thus far. Domestically, the FAA is responsible for civil avionics certification per the Code of Federal Regulations Title 14, more commonly referred to as the FARs for Federal Aviation Regulations. Part 21 of these FARs describes multiple certification paths. I'll only speak to one, which is based upon technical standard orders. A TSO is a minimum performance standard for a part used on an aircraft, and a TSO authorization is an FAA design and production approval for a manufacturer. The FAA thus far, since 1992, has published 7 TSOs for GNSS. I should mention that all the standards that exist today for GNSS that have been developed both internationally and domestically listed above are for L1 only avionics and actually primarily for GPS avionics. There's a little bit of standardization done for GLONASS, but by and large what you find for certified equipment around the world is mostly GPS only. This chart lists the 7 technical standard orders that the FAA has issued to date. The very first one was TSO C129, which was first published in 1992. This initial standard was for the use of standalone GPS as a supplemental means of navigation for aircraft. This standard is out of date now, and it has been recently canceled in favor of another TSO for standalone GPS equipment, which is referred to as TSO C196. The remaining standards include standards for antennas for GNSS, as well as for GNSS equipment that includes GPS augmented by either satellite-based augmentation systems, which include systems like the Wide Area Augmentation System in the United States, as well as equipment that's augmented by ground-based augmentation systems, or GBAS. Both SBAS and GBAS are differential GPS augmentations. SBAS is based upon satellite delivery of differential corrections and integrity data to the aircraft. GBAS is based upon a VHF delivery that is local to an airport or around that type of distance. For those of you that aren't familiar with TSOs, a TSO itself is a very short document, usually less than a dozen pages. They all invoke, however, lengthy documents that are referred to as MOPS in the practice. This stands for Minimum Operational Performance Standards, which are documents produced by RTCA, Inc. RTCA used to stand for Radio Technical Committee for Aeronautics, but they have since changed their name to formally be just RTCA. They are a private, not-for-profit corporation that serves as a federal advisory committee to the FAA. This final chart for my opening remarks is just a brief description of an RTCA MOPS. As mentioned on the previous chart, the MOPS are the heart of FAA GNSS and actually many other FAA TSOs. RTCA's GNSS MOPS are typically hundreds of pages in length and contain hundreds of performance requirements. These requirements address minimum equipment functionality, performance, and the environmental conditions that the equipment must function in. The MOPS also include test procedures. One set of requirements that I'd like to highlight on this chart are those specifying maximum tolerable levels of external interference. The GNSS MOPS include interference requirements spanning from 1315 to 2000 megahertz for the current suite of documents which only cover L1 or equipment which operates just at 1575 megahertz. These standards are harmonized with those in the ICAO standards. Based upon these requirements, the FAA concluded last January that Lightsquared's proposed use of the 1525 through 1559 megahertz band for 4G base stations was fundamentally incompatible with aviation use of GNSS. And I'll come back to this point in my second set of remarks. One last comment that I can't resist making on this chart is at a recent congressional hearing, the FCC characterized the Lightsquared GPS issue as involving, quote, unfiltered or poorly filtered GPS legacy devices. This statement is at best misguided. Consider, for instance, the aviation community perspective. Aviation GNSS receivers need to operate in a hostile environment. Next time you're waiting for a flight, take a look at the number of antennas on the aircraft. There are usually dozens, and several of these transmit at high power levels at L-band frequencies adjacent to GPS. For instance, at 1626 megahertz and above, many aircraft have satellite communication antennas within a couple meters of the GPS antennas on the roof. These SATCOM antennas are putting out hundreds of watts radiated power within that proximity to the GPS antenna. To cope with this amount of interference, most aircraft GNSS installations, in order to meet the performance requirements, include on the order of 4 to 6 stages of filtering, 2 typically within the antenna and 2 to 4 stages within the receiver. At this point, I'd like to hand the program back over to demos.
Thank you, Chris. Now, I guess Ron Bersato will talk about the performance standards from a wireless communications point of view. Ron?
Yeah, thank you, Demos. So, as Demos described, I'd like to give a highlight of the GNSS receiver standards and certification for wireless devices. But first, I'd like to start off with a who's who in GNSS conformance standard testing for wireless. So there's 2 major standards development organizations, both 3GPP and 3GPP2. The former one covers wideband CDMA, GSM, and LTE conformance tests, whereas 3GPP2 covers CDMA conformance testing. On the certification body side, there's 4 separate certification bodies. The first 2, GCF and PTCRB, handle LTE and legacy 3GPP technologies such as UMTS, GSM. However, PTCRB takes on more of a North American view. CCF covers the CDMA certification aspects, and CTIA, which is a wireless association that also has a certification program, has a test plan for wireless device over-the-air performance that also has a GPS aspect to it. So what types of performance standards exist in these test specifications? So wideband CDMA was covered in 34171 for A-GPS RF minimum performance. When A-GLONASS aspects were added, that required another test specification, which was 34172. All of the aspects for GSM, A-GPS, and A-GNSS minimum performance testing are covered in TS 51010. When LTE added A-GNSS aspects, the decision was made to actually combine the LTE and wideband CDMA aspects into the same specification, 37571-1. This was also done for the reason that we were able to also update the GNSS scenarios for both LTE and wideband CDMA. For CDMA, the A-GPS RF minimum performance is covered in C.S 0036-0, and recently that specification has also been updated to revision A to cover A-GNSS aspects. And then the CTIA OTA test is covered in wireless device over-the-air performance test plan. So typical A-GNSS minimum performance test specification covers both AGPS plus A-GNSS and A-GNSS only operation. It covers both UE-based and UE-assisted positioning modes. Now, UE stands for user equipment, and both of those positioning aspects rely on assistance from the network. But for the UE-based case, the UE is calculating its own position as opposed to relying on a calculation on the network side. Typical receiver performance tests cover nominal accuracy at high satellite vehicle power levels down to sensitivity levels, also covering dynamic range type tests where the signal levels for each satellite vehicle vary across the dynamic range, as well as multipath and moving scenarios. But in all of these test specifications, no additional interferers are presented to the GNSS receiver except for the supporting wireless radio bearer. So I've introduced the concept of a OTA test plan. Well, the typical OTA test system involves the use of a chamber. In this case, what's shown is an anechoic chamber, which reduces reflections such that the UE's antenna pattern can be assessed without undue interference, either from outside or interference due to reflections off of the wall. So you present the GPS signal level over a measurement antenna in the downlink, and you have a supporting radio link back to the whatever network emulator that is being used to support the radio connection. In the OTA test procedure, we need to actually take quite a few steps in order to get to a final result. So first we have to get the antenna pattern of the device under test. In this case, we're actually using the inherent measurement capability of the UE, and we use the satellite C to NO measurements from the GPS accuracy test. We can then compare the measurements that it makes across two independent polarizations in 30-degree increments in theta and phi, so that we get a good assessment of the antenna pattern. And then we linearize that data. In this case, correct the UE measurements with a known signal source. Since we have no idea about the UE measurement accuracy for any particular device under test, we have to normalize it so that we know our pattern data is accurate. Once we determine the peak of the pattern, we can then go use the same GPS sensitivity test cases from the minimum performance standards, and including the satellite scenarios and the performance metrics. This allows us to provide traceability to the OTA test back to the conducted test, but in this case we actually search for the value as opposed to testing one particular value. Then with these two quantities, we now have an EIS pattern that we can calculate spatially averaged quantities from. So in this case, the traditional term, total isotropic sensitivity, or in some cases referred to as TRS on the 3GPP side as total radiated sensitivity. But in either case, it provides an average quantity for the entire pattern as to how well the receiver performance exists. And then we have other partial quantities like upper hemisphere and partial isotropic GPS sensitivity to have an idea of how the device performs in any one particular dominant direction, like looking up to the sky in the upper hemisphere case. And then in addition, OTA allows us to do testing of additional interference aspects within the wireless device Some interference aspects couple in different mechanisms than conducted tests that are used in the performance standards from the other certification bodies. So in the OTA case, we can actually evaluate the GPS performance at different wireless radio operating frequencies and compare that performance against the reference frequencies we used for the full OTA measurement, thus understanding if there's interference issues at any particular network conditions. Back over to demos.
Thank you, Ron. All right, so we'll take a pause now to allow you to ask questions to the experts. So if you have any questions, please send them in. And let's see, we do have some questions here. So let me start with the first one. This one is for Jules, and it's from Bruno. And it's asking, why only mention GPS when GPS and GLONASS, when Compass and Galileo are coming on the GNSS scene? Jules, do you have, do you want to answer that one? Do you want anything to say about that one?
I guess the only reason to limit the discussion so far is because GPS and GLONASS are currently the only active, fully capable GNSS services available. Of course, the same issues will affect Compass and Galileo as they become operational, particularly in the very challenging L1 portion of the spectrum. But so no particular reason to limit to GPS. And I guess I intended the GNSS connotation to cover the remainder of the global navigation systems, both extant and in the future.
Thanks, Jules. Well, the same question for Chris. Is there anything from an aviation perspective that you would like to add to that?
Yes, from an aviation perspective, the reason I mentioned only GPS and GLONASS is because that's all that's covered by the existing international and domestic standards. The aviation community is very interested in both Beidou as well as Galileo, and they do have on their work programs both domestically and internationally in ICAO, RTCA, and other standards bodies to develop standards to allow aircraft in the future to use the signals from those systems as well. So there's interest. I only omitted it just because they're not within the current standards that I attempted to summarize.
Okay, well, and while we're at it, I'll pose that question again to Ron. Is there anything on the wireless side that you'd like to add to that?
No, I think it follows kind of along the same lines as the previous speaker's answers. Essentially more a timing issue, and the other two have been more readily available in, say, chipsets, devices, and for setting the performance standards. So I think it's more just related to timing. So I expect they'll be coming soon as they make their way into more platforms.
All right, thank you, Ron. All right, so the next question we have is from Rakesh, and I'm going to point it to Chris here. And the question is, do we have standards for software-defined GNSS receivers?
For aviation, we do not. Our standards do not tell the manufacturers how to build the equipment. They are the aim is for these to be performance-based, just what performance requirement the equipment needs to meet. So in practice, somebody, or in principle anyway, somebody could build a software-defined radio that met the current TSOs, for instance, domestically here. There would be perhaps some difficulty in doing this. There are some rigorous standards on software development that are invoked by the TSOs, other RTCA documents, including what are called document number 178, as well as hardware document 254, that invokes very rigorous process for the development of software and complex hardware.
Ron, is there anything along those lines that from the wireless side of the house, software receivers, that you want to add?
No, I think that's fine.
All right. Let's see. So the next question, and it's going to be for Ron. The question is, well, again, it's why does Global-Star allow transmissions 30 dBm directly adjacent to the GLONASS band? Do you have anything, or is that any comments on that?
So in this case, a lot of that ends up being related to what their expected ground level power level is for the purpose of a wireless device testing. So a lot of the same assumptions were used in some of the Lightsquared effort that we'll be talking about later, where we can actually determine the performance impact using adjacent channel interferers like is described here, and actually arrive at clear conclusions as to the impact of said transmissions.
Thank you, Ron. All right, it looks like we have time for one more question, so let's see. This is a question from Blaine, and I'm going to direct it at Chris. And it says, from a federal regs point of view, and from the aviation point of view, if anyone generates a non-GPS continuous wave signal above the line on the chart you showed, are they wrong? Are they in the wrong?
That's a complicated question to answer. The bottom line is that anyone transmitting at any frequency needs to be in compliance with either the FCC rules if they are a non-federal government entity, or with the NTIA rules if they are a federal government entity. The MOPS curve that I showed earlier is basically for received power levels, but those regulations, the FCC rules and NTIA rules, both of which are in Title 47 of the Code of Federal Regulations, would have all the what's okay and not okay in terms of transmitted power levels and other bands across the wide span of frequencies that are covered by the RTCA MOPS. I would mention also that if you put the signal directly in the 1559 to 1610 megahertz band, the desired band for GNSS, that's a so-called prohibited band, and you're not allowed to broadcast in there, period, unless you are a GNSS entity with the authority to do so.
Thanks, Chris. All right, so let's move on to the second half of our webinar, and then we'll have a chance later on for more questions. So next, I will hand it over to Ron, who's going to, I guess we have one poll question before we go into that, and let's take that poll question. So, Lori?
We would like to know if you agree or disagree with the following statement. Standards and certification are important so that I don't have to worry about performance details. So let's take a look. Looks like disagree came out 55%, with 45% agreeing. And any thoughts on that, Demos?
Almost split in half, and I guess it's going to depend. So I guess with the topics that are going to be discussed next, we'll partly be addressing some of this. So with that, let's move on to the next set of presentations, and I'll hand it over to Ron to talk about the second part of the wireless side of things. Ron?
Okay, thank you, Demos. So first up, I'd like to kind of go over some lessons learned in specific use cases. So starting with the Lightsquared effort. So if you go back to the first part of my talk, I mentioned about the A-GNSS performance standards that we had. We're really testing A-GNSS aspects only, and not really aspects related to outside interferers. Well, in the case of the Lightsquared spectrum deployment plans, the request was made to actually try to determine the impact of this deployment plan on existing wireless devices on the market. And so there were a couple different phases for the deployment plans. some related to a 2 by 5 megahertz LTE carrier deployment, and some related to a 2 by 10 deployment, which also later got extended to just a lower 10 option. So what we did as part of the Cellular Technical Working Group was we developed a test plan to evaluate the GPS performance impact of these LTE downlink signals. So we created receiver blocking and intermodulation test scenarios that were representative of the last slide. We used realistic interferers using signal generators. So we duplicated the frequency allocations, we duplicated all three spectrum options that I mentioned. We also duplicated the LTE downlink modulation coding schemes, as well as being able to vary the interferer signal levels to determine the failure points. This allowed us to also base the test cases for the AGPS performance on existing industry test standards. So our impact was immediately traceable to defined performance criteria. And with this, the Cellular Technical Working Group concluded that the lower 10 megahertz plan did not cause harmful interference to cellular AGPS operations. So next I'll go over the specific use case associated with LTE band 13. So LTE band 13, which is part of the FCC upper 700 megahertz band allocation, which is also referred to as upper C block, happens to have a UE transmit configurations where the carrier frequency is at 781 and the RF channel bandwidth actually occupies actually around 9 megahertz, but it's called a 10 megahertz RF channel bandwidth in the standard. So this leaves the last allocation of the channel at 786.5 megahertz, which makes the second harmonic of that fall at 1573 megahertz, which is very close to the GPS band. So any out-of-band emissions from that transmitter would spill over to GPS. Thus, this highlights the need to evaluate GPS performance with specific transmit configurations. So what are the possible future GNSS performance standards? Well, one is we could consider adding the interference testing, which I described in this lessons learned in specific use cases, by adding receiver blocking and intermod tests with realistic interferers. Can also expand the OTA testing to include additional interference sources such as multi-radio operation within devices such as Wi-Fi and Bluetooth and such. As I mentioned before, OTA does pick up on aspects of interferers that aren't necessarily covered in conducted testing, as well as we can try to apply some of the same testing concepts to other GNSS market segments as necessary. However, of course, any additions would require necessary work items in the representative standards and certification bodies, because those bodies need to determine and consider the workload associated with developing those standards, as well as the impact to certification tests to the industry. And with that, I'll turn it back to Demos.
Thanks, Ron. All right, and we're going to hear now from Chris on some further thoughts on the issue. Chris?
Okay, thank you, Demos. In my second set of remarks, I'd like to address recent recommendations for more widespread use of GNSS receiver standards, in fact, to the extreme and all-encompassing mandate in order to promote spectrum efficiency. This first chart has an abbreviated history of some of the proposals or discussions that have taken place on invoking receiver standards for the purposes of spectrum efficiency. I expect that most listeners are familiar at least with some of the recent activities listed on the chart. These include Lightsquared's request and February of last year for the FCC to initiate a proceedings to develop rules for GNSS receiver interference tolerance standards. Later last year, this similar subject was taken up by the President's Council of Advisors on Science and Technology, who produced a report on their findings. It was also addressed in a congressional hearing on the role of receivers in a spectrum-scarce world in November. And then finally, I think we're all looking forward to a report by the U.S. Government Accountability Office, which is due in February on this topic that was mandated by Congress per some legislation from last year. What some listeners may not be aware is that this topic actually goes back even further than that in time. Way back in March 2003, going back to my very first bullet here, the FCC issued a notice of inquiry in the United States asking the public whether they should broadly adopt regulations on receiver interference immunity standards. This docket was kept open for 4 years, and finally the FCC decided to close it without undertaking such a broad action. I'd like to offer some personal observations regarding these recent proposals. In a nutshell, I do not recommend widespread GNSS receiver standards to promote spectrum efficiency. Receiver standards are onerous. They certainly have proven to be very beneficial for aviation safety. They've also proven beneficial to many other communities who like to do it, for instance, for reasons having to do with parts interchangeability. But their general imposition on all GNSS products would, in my view, needlessly stifle innovation. Another point that I'd like to make is that the existence of standards, unfortunately, is not sufficient in itself to avoid radio frequency compatibility issues. And just to give you one example, the aviation standards that I mentioned in the first segment of my remarks, those standards were largely in place. At least the interference mask that I showed in my last chart were all in place before 2001, when the FCC initiated the rulemaking on MSS ancillary terrestrial components, which is basically permitting services along the lines that Lightsquared proposed of terrestrial 4G network in the bands adjacent to GPS. Unfortunately, the existence of these aviation standards did not stop the regulatory process from proceeding into the mess that we found ourselves in. If this experience teaches us anything, it should teach us that receiver standards are not sufficient by themselves. Agreements on a lot of other factors, minimum transmitter receiver distance, propagation loss models, and methods to aggregate the effects of multiple transmitters are also necessary components of any radio frequency compatibility study. And in my view, those are some of the harder pieces that need to be addressed. Lastly, it is not a reasonable expectation that all GNSS receivers can conform to one interference mask. There's a wide variety of capabilities, as the user audience here is aware of. And that variety is actually going to continue to grow as we see future satellite navigation systems deployed. Not only the capabilities are going to vary, but the requirements on size, weight, power, and cost of the equipment will also vary. Just to give one example of how this might come into play for interference requirements, the International Telecommunication Union, which is our international spectrum regulator, has recommendations on protecting GNSS systems from emissions in their desired band of 1559 to 1610 megahertz. And these recommendations define 11 distinct receiver classes. Not an easy thing for our regulators to keep track of if we need that many or more for adjacent band systems. My final chart is just intended to emphasize my previous comment on the difficulty of developing one interference mask to protect all GNSS equipment. This chart shows 4 radio frequency filter technologies that are commonly used within GNSS antennas and receivers. Down at the bottom is an example of a cavity filter. These are widely acknowledged to provide the best performance of any filter, but are rarely used because of their extreme size and weight. Up top, we do have filter technologies that are kind of the workhorse of the industry. For high precision equipment, most vendors are most comfortable using ceramic filters. They provide good performance as well as well-controlled differential group delay, going back to Jules' point on the need in navigation, not just to demodulate bits, but also to estimate the precise time of arrival of a wideband signal. Mass market users like SAW and BAW filters. These BAW filters in particular, which stands for bulk acoustic wave, have made tremendous performance strides in recent years, but as compared to ceramic filters, are more sensitive to temperature and do not have as well-controlled differential group delay. That concludes my remarks. Thank you all for your attention, and I'll now hand the program back over to Demos.
Thanks, Chris. All right, and our final presentation is going to be once again by Jules McNeff. So, Jules.
Okay, thank you, Demos. And in this section, I'll look at receiver certification possibilities in slightly more detail and provide some recommendations for the two main protagonists, the regulators and manufacturers, going forward. As a quick review, there are two principal categories within which to apply GPS receiver certification. The first is technical certification of the GPS receiver elements only against the parameters specified in the GPS signal in space interface specifications issued by the GPS directorate. And here I mean the performance of the GPS receiver in dealing with the bit structure and the requirements to translate it and process it to produce the ultimate navigation message for the GPS receiver component. The second category is performance certification for GPS devices that are themselves integrated in applications packages against performance standards that are developed by application standard bodies. There is also, of course, certification of security components, but that applies whenever restricted access measures need to be employed to prevent access to or disruption of the PNT information. I've highlighted a couple particular factors that are relevant to interference susceptibility for the first two categories. With respect to a certification process in general, the first issue to address is the scope of the desired certification. Will it encompass only one or both of those principal certification categories? And that is if performance parameters have been established by a competent and recognized application authority. Then, what will comprise the certification criteria, and will it be necessary to establish consensus across an application community for common criteria? For example, will they look at component level performance versus integrated system, or the component integrated in an application system? Also, will they allow consideration of multi-frequency benefits or limit performance requirements to single frequency performance? And if consensus is required, how will that be accomplished? At the same time, a process model needs to be determined that best applies to the particular certification task. In cases where government rulemaking defines performance parameters, some form of government participation in the process will likely be necessary. This can include government-conducted certification or government oversight of manufacturers' testing in accordance with government-provided specifications. Such models are used by the FAA and are being evaluated by the DoD, the Department of Defense, in its own consideration of certification for military receiver performance. Alternatively, the process can involve industry-conducted certification in accordance with industry standards as applies to wireless devices. And today you've seen examples of both. In any event, it's evident that additional performance certification efforts will likely be required of GPS manufacturers, particularly in cases where GPS contributes to safety of life operations and to U.S. critical infrastructure. The roles of government and industry will be different in defining the way ahead, but they don't have to be in conflict. As it proceeds with plans to impose performance standards or certification requirements, government must be consistent and open about the policies and process. Such standards as may be imposed should focus on preservation of critical application-specific GPS services and not attempt across-the-board, one-size-fits-all implementation that would stymie industry innovation. Also, the rulemakers must take account of all available GPS capabilities, not just those at L1, and make allowances for the signal reception and processing requirements that remain unique to GPS and other global navigation satellite systems that I spoke to in Part 1. The role of GPS industry and of the users, frankly, in facing expanded performance certification requirements should be to shape the environment rather than resist the initiative. Industry must commit to limiting operations within GPS-assigned spectrum and making use of all available GPS civil signals necessary to improve interference mitigation for specific applications. GPS industry should take the lead in developing consensus on an application-based certification framework that focuses on specific GPS receiver types used for safety and critical infrastructure, much like other industry associations have done. Perhaps the U.S. GPS Industry Council, or its current instantiation, the Coalition to Save Our GPS, could begin these initiatives among its membership. In fact, note parenthetically, I made that suggestion to its members during the formation of the Industry Council over 20 years ago. Finally, as I said at the beginning, all GPS manufacturers and users must constantly remind government regulators of the unique nature of PNT from both PNT and GNSS from both technical and operational perspectives. Clear and supportable quantitative arguments, such as those marshaled by the FAA during the Lightsquared controversy, are most useful to roll back institutional reluctance to affording special consideration to GNSS signals and services. And while it's true the quantitative performance standards won't prevent others from having interest in adjacent spectrum, having quantitative performance testing and demonstrations will in fact help to turn the tide, as we saw with the FAA's experience in the last during the Lightsquared issue. So with that, I conclude my contribution. Thank you all very much for listening, and I'll turn the proceedings back to Demis.
Thank you, Jules. All right, so let's see. Before we move on to further questions for the experts, let's take one more poll. And you can put the poll up, Lori.
One more chance to weigh in, folks. Would like you to agree or disagree with the statement. Testing to a standard would reduce test time development and save development costs. Let's take a look. Okay, looks like our front runner is agree at 72%.
Okay, and again, I guess there's a decent amount of the audience that disagrees, so that would make, I guess, for some interesting questions for the experts later on. All right, so moving on, before we move on to more questions for the experts, some next steps here. So on this slide, we have some contact infos. If you, we have the contact info for Spirent, the sponsor of this webinar. Also, there's going to be the website at the bottom of the page where we will have the PDF of today's presentation, and some list of resources will be available. All right. With that, I guess we're into our second session for questions. And again, we have several questions that have come in. The first question is going to be, it's from Dean, and it's for Ron. And it's, what is the time frame for the 3GPP, 3GPP2 standards address the newer constellations such as Galileo and Beidou?
So that's a good question because I don't have an answer for it, but I would have to say that right now 3GPP in 37571 does have essentially a placeholder for the Galileo aspects and has left the aspects for future study, which would mean that in the end member companies would have to come back with contributions to address those. For Beidou, there's some test aspects of the ICD that were released some time ago, and I guess the full ICD was just released, so it will be hard to say as far as exact timing, but I would expect that now, since the full ICD is released, that that if member companies did want to introduce work items for that work, then they could get started in those bodies.
All right, thanks, Ron. Let's see, this next question is from Bruno, and it's going to be, well, I'll pose it to Chris. And the question is, it seems that to go beyond already published standards on terrestrial transport applications like intelligent ITS applications, possibly using GNSS, we should consider a generic model of location systems, application layers, and associated environments in order to derive requirements and standards. What's your opinion on this? Do you have an opinion on this?
Yeah, so for ITS, intelligent transportation systems, it's certainly not an area that I've done much in, but as I've read, I guess in Nevada and California, for instance, they are allowing autonomous vehicles to operate. For me, this would seem to be a natural application that would benefit from standards. Going back to my remarks, I'm not in favor of mandating standards for all, but this would seem to be one where you would want to have uniform performance standards to ensure safety in particular.
Thanks, Chris. All right, let's see. The next question is from Jeff, and I'm going to pose it to Jules. And the question is, does the panel, and I guess I'm posing to Jeff, but Jules, but I'll ask the others, but does the panel believe that GPS is adequately protected by present FCC emission rules for cellular devices?
In a nutshell, I would say anyway, I think we don't know enough yet at this point about the deployment of cellular devices to answer that question for sure. I mean, during the Lightsquared controversy, there was a lot of discussion about the Lightsquared ground-based transmitters below 1559, but virtually no real discussion or testing about the effects of the handsets above 1610, and so I don't believe there's enough information known about the performance of the cellular devices themselves to say with certainty that GPS is adequately protected by the current rules.
All right. Ron, did you have any comments or anything you'd like to add to that, or from your experience in the wireless world?
Yeah, I'd have to say I agree with Jules' assessment there. I think that with the handset side, you do have to get into particular aspects as related to proximity. So now you have to make assessments and judgment as to proximity of wireless devices to other GPS receivers in order to define adequate performance requirements there. And I don't think that work has been done yet or adequately assessed yet.
Great, thanks, Ron. All right, so let's see. The next question is, let's see, from it's from Tony, and I'll pose it for Jules. And he asks, we've been talking about the U.S. response to the generation of standards. Do you foresee a number of standards nationally based, for instance, standards in US, Europe, China, Japan, etc.?
Well, at the outset, I've really focused my attention on what happens in the U.S. And what U.S. industry and the U.S. regulators elect to do going forward, because the question of standards is still being discussed by within the regulatory community, and industry certainly has an opportunity to take some initiatives on its own that can affect things within the U.S. Now, things in the U.S. or in other nations, frankly, eventually percolate internationally, either through other individual national groups or into the ITU. But at the moment, I was just focused on things that are happening within the U.S. itself. I hope that answers the question.
Right. Thanks, Jules. All right. So the next question is from Kazimieras, and I think I'll address it to Chris. And again, you're the closest to aviation, so this is on an astronautics question, is what are the standards on GNSS receiver and astronautics applications? Do you have anything to say about that or any experience with that?
I don't. I guess I've run into space applications of GNSS over the years, but I'm not familiar of any prevalent standards that are in use for them. They vary tremendously, of course, in terms of performance that they envision or require from the GNSS sensor, depending on exactly where you are in space, whether you're in low Earth orbit, below the GPS satellites, above the GPS satellites, or somewhere in orbits going through them. So my experience has been that for the most part, people develop their own mission requirements for such equipment, but I'm not familiar with any widespread standards.
Thanks, Chris. All right, let's see. The next question is from Sarang, and I will, let's see, pose it for you, Ron. And the question goes as, while I agree that it's difficult to standardize GPS receivers over diverse application areas. However, would it be more beneficial and practical to standardize instead the receiver performance testing procedures used by manufacturers?
Yes, thank you. Thank you for this question, because I think it does allude to some of the comments I made at the closing of my talk. I do think it would be beneficial to standardize at least the testing procedures, because then it would be something to allow similar aspects of the GPS and GNSS aspects to be evaluated. Now, maybe the performance limits change depending on application, but I do think there would be inherent benefits to the industry if we are going to extend or try to extend the performance testing into other areas to eliminate some of the concerns about additional test time, complexity, and cost. I think this is one way to help alleviate some of those concerns if we can leverage well-known test procedures. So thank you.
Thanks, Ron. All right, let's see, the next question. Let's see, so this one actually could be posed for several of our panelists, but let me start with perhaps Steve. Do all manufacturers comply to interface specifications, and why not? What are the benefits or consequences? Now, I guess I could address this one to all the panelists and see what they have to say, but Steve, I'll start with you. Do you have anything on that one?
Yeah, it's an interesting question, and I think the answer is obviously they comply to the signals in space ICD. They're required to do so in order to have a receiver that works, but that's about it. In terms of any other interfaces that they have, no, we're not yet in a sort of plug and play commoditized market for GNSS receivers. So all manufacturers don't comply to any particular interface specification.
Anything you would like to add to that, Jules?
Well, I guess the only thing I would add is sometimes, and I won't cite any specific cases, but there are even times when manufacturers don't exactly follow all of the interface specifications, for example, in how navigation message bits are used or plan to be used, and so sometimes we'll find out that an application fails, and we learn about it through the GPS Operations Center or wherever, and then on going back to triage the issue, we find that there's some sort of problem in the receiver and how it's processed or handle the navigation message such that it locks up or fails in some way. And so that's why that part of it's important. On the other side, that's right, once you get into the sort of more qualitative application performance regime, manufacturers follow their own instincts a lot of times, and so some additional rigor might be useful, again, depending on the importance of the application to public safety or economic infrastructure, etc.
All right, thanks, Jules. All right, so let's see. Well, I think this one is kind of related to the question that was just asked, so I'll again pose it again to Steve and perhaps Jules and Ron afterwards. But the question is, are there industry standards for high precision GPS? Steve?
Yeah, it's a good question, and I'll sort of refer back to some of the stuff that's been mentioned before in the presentations, and Jules had a chart where he talked about technical specifications and performance specifications. So if we're looking at high precision GPSs such as surveys or precision agriculture or whatever, these guys will normally specify their performance in parametric terms, and the way in which those parameters are defined and measured is pretty much up to them. So doing a true comparison between different vendors is quite often fraught with difficulty. And so even though they're quoting performance, they were not necessarily measured in the same way. So I guess the short answer is no, there aren't really industry standards. And to Ron's point on the standardization of test procedures, I think we'd probably be in a better place if there were, at least around measurement methods, techniques, and parameter definitions.
Well, posing the same question for Chris, I mean, would you consider aviation applications high precision or high integrity, or are those synonymous? And would you have anything to say on that aspect, on that question? Are there any standards?
Yeah, I guess when I hear high accuracy, I think of more survey grade applications that are relying on integer ambiguity resolution to get down to the centimeter or millimeter level of accuracies. Aviation isn't quite to that point, and for aviation applications, the accuracy demands aren't that stringent, but the integrity demands on making sure that you never ever have a bad position output from the box, that is far off from truth without an alarm being thrown concurrent with it is of paramount importance. So our standards emphasize really the safety aspect over the accuracy aspect.
All right, thanks, Chris. All right, let's see, the next question. I'll pose this one for Jules, and it's from Dominique. And the question is, undoubtedly, spectrum is in demand. And so what can the GNSS community do to assure regulators and terrestrial operators that we are using spectrum efficiently?
Well, thank you. I think the answer to that was really in my last slide, that the radio navigation satellite service allocation from the ITU spans 1559 to 1610 megahertz, and it's divided up according to how the various GNSS providers have registered their services to operate. GPS is registered basically between 1560 and 1590. GLONASS is at the upper part of the band. Galileo and Compass are sharing other portions of the band. And so ultimately the proof for fighting off interference effects within the band rests in a quantitative argument based on how quantitatively the users are using that their allocated and registered portions of their spectrum for the applications that their GNSS services support. And again, quantitative arguments, in my view, will overcome anecdotes and assertions every day, but they need to be put together and coherently delivered when the time comes.
All right. Thanks, Jules. All right. Let's see here. The next question is from Bruno, and I guess this could be for anyone on the panel, but I'll start with Chris. And it's more a remark on your observation. Chris's observation, this highlights the need for a standardized class of receivers based on performance, including robustness and interference. Any comments on that? Do you want to expand anything on that or say anything to that, Chris?
Yeah, I guess, again, my view is that I don't think we should be mandating receiver standards for application communities that aren't interested in them for the sake of cramming systems into bands adjacent to GPS. I think that for those purposes, just a traditional rulemaking procedure is adequate on describing what the transmissions look like and all the rules applying on the transmitter side. If performance standards are developed, there certainly are many different types of receivers, and whether they're voluntary or mandatory for certain applications, then absolutely I guess agree that that standard will need to be divided up for different application classes. There's very different demands being made on GNSS by different members of the community.
Thanks, Chris. All right. Excuse me. Let's see, the next question here, let's see, again, this could be for a couple of our panel members, but I'll start with Jules, and it's from Sarang. And the question is, when, I guess Chris and Jules could probably say something to this, is when and by whom was the Lightsquared interference problem first reported?
Well, my recollection is that it first sort of became evident in late summer of 2010 with some notifications that came out of the FCC. It was first, I guess, recognized and reported by the GPS industry folks in, I want to say, October or so, November maybe, when it became evident that the FCC was moving smartly toward a rather peremptory rulemaking in favor of this Lightsquared initiative that had sort of popped into view in the late summer, though it was in work for some time before that.
Anything you want to add to that, Chris, or is that?
Yeah, I guess it's similar to Jules. My recollection as it was that that fall of 2010, and really, I think the GNSS community didn't get fully engaged until the FCC published the license modification request from Lightsquared around Thanksgiving of that year, when all of a sudden it became widespread what a problem this would be. Garmin and others, I guess, provided some early materials and analysis results that suggested this could be a real big problem, and then things really took off the next spring.
Right. Thanks, Chris. Let's see. Next question. Again, well, I'll give this one to you, Chris, as well. It's from Arun, and he's asking, they're asking, is interference from Globostar and Iridium on the agenda for defining receiver standards? For us, it's an increasing problem on board vessels and for high-performance GPS and GLONASS receivers.
I can't speak broadly, but at least in terms of in aviation bodies, RTCA and other standard bodies do look at all transmitters and where they'd be located and the coupling between their transmissions and the GNSS receiver, and that's done nearly continually to result in, at this point, mostly in restrictions on the transmission side, or what kind of filtering would need to be done on the transmission side to ensure compatibility. The reason now why it's mostly the transmitters that need to be fixed is just because we do have a very large installed number of receivers, and most folks are reluctant to impose any restrictions on the receiver end, given that we're as mature as we are. But beyond the aviation community, I'm not familiar, I guess, with maritime or other applications as to whether that problem has been addressed through standards there.
Right, thanks. Let's see here. I think it looks like we probably have one time for one more question. And so let me try to pick a question here that would be could actually address in the time we have. And I guess I'll direct this one to Ron. And the question is, what means are used to ensure or enforce compliance with various wireless A-GNSS performance standards, given the level of competitiveness within that industry?
So if we go back to some of the discussion around the standards development, we have standards development organizations that develop these performance standards. Those performance standards are developed based on opened work items that are agreed within those standards development organizations, not only at a working group level, but also at a plenary level. So it's understood as to what the overall work effort will be and what the impact to the wireless industry will be. Then the certification bodies, the four that I showed earlier, then also make their own assessment based on the test standards that have been put in place, and specifically identify for their particular market what particular test cases to validate and to enforce as part of their certification programs. So I think it's those two aspects which both ensure and enforce compliance, but at the same time also allow the different certification bodies to address the competitiveness issue by being flexible at both levels.
Right. Thanks. Thanks, Ron. Let's see here. I guess, well, one more question, and I think we'll probably have to stop here. So let me see. And the question could be actually to anyone on the panel, but I'll start with Jules. It's from Dominique, and it's where might the next Lightsquared frequency be? Is the question.
Well, we don't know. I mean, we've dodged two bullets already. The first was in the early 2000s with ultra-wideband, and ultra-wideband was everywhere. And then Lightsquared came along, and it was much more focused both below and above the L-band. So wherever the next potentially useful spectrum that someone thinks might be, quote, underutilized is, so likely where that'll show up.
All right. Thanks, Jules. I guess for the sake of time, we're going to have to stop at this point with the Q&A. And I guess I will hand it over to Lori. I guess we probably have a word from the sponsor, but Lori?
Okay, yes, absolutely. Folks, it is time to wrap things up, and we'll go ahead and do that by inviting Steve from our sponsor at Spirent to leave us with a brief word. Steve?
Okay, thanks, Laurie. Well, I have been really impressed with the quantity and inventiveness of some of the questions, and so it's certainly been, for me, a very interesting and useful event. The other thing that I particularly took away was how over a range of contributors from disparate backgrounds, there's some real consensus around the value of standardization and at the same time an appropriate sort of caution that one size does not fit all. Comment was made more than once. So for me, this has been a really interesting event. I've certainly learned something, and I hope you guys have, and thank you very much for attending. Laurie?
Okay, folks, and before we sign off, would like to thank each of you for joining us and trust you found today to be of value. Want to offer special thanks to Jules McNeff, Chris Haggerty, and Ron Brasado, and of course to our sponsor and co-host Spirent and Inside GNSS. And folks, you will be receiving a short survey at the end of the webinar, so would appreciate you taking a moment to fill it out. Would also like to give a thanks to our logistics producer, Patty Van Hooser, for her behind-the-scenes collaboration and support. And again, a copy of today's webcast will be available for download, and you'll be receiving it in the way of a link but via email early next week. And most importantly, thank you again for joining us. This is Lori Dearman saying have a great rest of the week. Bye for now.